Hello and welcome to the third and last session of the CFD Master Class presented by SimScale. I'm very happy and glad to see so many participants again who want to take the final lesson of this course. And as you know, before we start to actually talk about today's topic, I would like to make sure that everybody can hear me loud and clear. So in the case you can hear me, please raise your hand. Virtually for sure. Great. Seems like everybody can hear me. In the case, for example, the audio connection should drop or the quality is not good, you can also use our toll-free audio service number, which you can see right now on your screen. Right. Yes. Today we will talk about multi-phase flow simulations, which is really, as I would say, a more kind of advanced simulation type. And today you will learn some really important fundamentals to understand what's the difference between a single phase and a multi-phase simulation. Then we will do a live demonstration, and after that I will present your homework to you, and we have for sure again the Q question and answer session. If you have questions, just write them down to the question box and I will try to answer them as quickly as I can. Okay, and therefore let's start to talk about some fundamentals. And first of all, I would like you to take a look at the current slide where you can see three different examples for a multi-phase simulation. And in the end, there are a lot of definition what a multi-phase simulation is. But basically, the difference between a single-phase simulation and a multi-phase simulation is that in a multi-phase simulation, you have different fluids which are interacting. Compared with our CFD simulations where we just used air all the time, that means you have, for example, a liquid and a gas, but this can also be two liquids with some mixing. And here are three examples which you can see. For example, in the middle you see a simulation of a race car fuel cell, and actually what was simulated is how the fuel is moving in this tank during cornering, which we call a sloshing simulation. Or another good example is the simulation of this offshore oil plant. Because if you think about it, on the one hand you have the interaction or the aerodynamic of this platform, so the surrounding air and everything which is outside the water. On the other hand, you have also hydrodynamics between the water and this this lower part of the offshore plant. And everywhere, as I mentioned, where we have two different phases together, we call it a multi-phase simulation. And therefore you need a dedicated kind of solver which is able to manage these several fluids at the same time. And there are a lot of methods how to realize multi-phase simulation. At SimScale right now we have implemented the most common, which is called the volume of fluid method. If you are more familiar with CFD, I'm quite sure you will hear this term in the past, or you had heard this term in the past. And let's make it very easy and take a look at the first equation. Basically what we do, we introduce an additional variable, so which we call alpha. And alpha describes which fraction of the cell is filled with which fluid. So if alpha is 1, it means we only have phase 1 in the cell. If alpha is 0, we only have fluid 0. No. And basically the volume of fluid method takes the standard equations we use for single phase simulations. So it takes the conservation of mass, momentum and energy, and adds one additional equation, this one, and in the end we're introducing alpha as an additional variable and we solve it. And how it's working basically, let's just take a look at this to understand really what alpha means. Because alpha is just describing the volume fraction. Let's imagine what you can see here would be a domain, and the gray part of the domain is a water droplet, and the white part is the surrounding air. Then 1 means that the full cell is filled with water. 0 means this full cell is completely filled with air. And 0.4 means you have both. And 40%, 60% of the cell is filled with water and 40% with air. And based on this, it's very easy, or not so easy, but it's simple to create a flow simulation which is able to handle this multiple fluid fractions we have, fluid phases we have. And there is another very important thing I would like to talk with you about today. It's a so-called CFL or Courant number. Basically, it says the Courant number can be calculated for each cell, and it's defined as the product of the local velocity in the center of the cell multiplied with the time step divided by the length of the cell. And if we now think about it, if we multiply a velocity, a constant velocity, with a time step, and since we're doing numerical simulation, discrete simulation, the time step is not changing, then we get out a distance. If you, let's say, the flow velocity 5 meters per second, and you have a time step of 1 second, you have 5 meters, which means your physical domain, this waterfront, this wavefront, will move 5 meters during one time step of 1 second. And delta x is the length of your cell in flow direction. And this must be smaller than 1. So what this CFL number basically expresses, this equation tries to say, is that for multiphase simulation, which is by the way in any case is transient, you must make sure that the relation between time step or between physical domain and numerical domain is smaller than 1. In the end, just to understand why this is important, just imagine it's bigger than 1. That would mean that the fluid is like faster than the numerical discretization of the domain. And then the simulation cannot be stable. Just imagine, if it's faster than 1, then the whole fluidity left the cell before the end of the time step. And that makes it impossible to solve the computational domain then. Okay, great. Then I think you learned a lot. And since this is something completely new, I think the best is to learn while doing it. And therefore, let's switch to the simulation designer. And I've prepared a nice project we'll take a look at today. It's basically a waterfall, which you can see here. And what we are doing, we want to simulate a waterfall. We have a step. The fluid, the water, is entering this domain with a given speed of 2 meters per second. And then we have the step. And we want to know this free surface, we want to know about the free surface of the waterfall, and also about velocity, flow velocity, pressure, etc. And first thing we have to do, therefore, is we will open a project I've prepared, including only the geometry. And we will now create the simulation. First of all, let's take a look at the geometry again. As you see, we have a length in the x direction of 15 meters, in y direction of 3 meters, and a total height of 6 meters. And what we want to do right now is to create a mesh. So we will choose the geometry waterfall, confirm the selection, and add a new mesh operation. We will use the hex dominant parametric mesh operation and click on Save. First of all, we have to create a bounding box. And here the good thing is that SimScale is automatically suggesting a bounding box based on the application. And in this case, since the geometry is also very simple, this base mesh box is perfect. We just click on Save. And next thing is, if you remember how SnapPX mesh is working, we have to define, first of all, a base mesh size by giving the number of elements we want to divide this base mesh box into x, y, and z direction. So for x direction, and here we can also keep it like it is. You can calculate the actual mesh size very easily for level 1. For example, we have a total length of 50 meters in x direction, and if we just calculate it, therefore, our initial length in x direction, for example, is 0.13 meters. This is also fine. And if we take a look at the material point, this is basically also fine, because if we visualize it, this material point is inside our geometry. We can see it here. Just a general trick. I would recommend not to use such values. I would more use values like that. The reason is very easy. Just imagine in the case that your material point is exactly at the interface of two cells, that can create problems sometimes. But this is just an expert trick. It does not have to fail just because of that. And what we can do right now is we will first of all add a refinement box, which we'll later on use. And then we'll just create it based on the coordinates. And we will create a refinement box here, because here we expect to have a lot of change high gradients. Okay. And yes, finally, we can just have to modify, add some refinements. And let's see. So first of all, we will create a very general refinement. Call it surface refinement. Apply it on the whole geometry on level 0 to 1. And we will add a region refinement. Apply to the Cartesian box. And there we want to have a cell level of 2. Great, finally we just have to adapt some settings. So we will change first of all this value from 3 to 4, number of cells between level. What does this setting mean? Let me try to explain it to you in very easy words. In the end, as you know, based on the level, I'm splitting my cells. But if the increase or decrease of cell size is too high, that can create problems. Therefore, we will introduce some buffer layers between different cell size regions, and we just increase it from 3 to 4. There is a question right now by Zaid, and Zaid wants to know, why did you apply to a level of 2? Zaid, I think you're talking about the region refinement, right? The reason is, if you take a look at the physics, the water will enter here, and you will here have the waterfall, and therefore we added this refinement so to the waterfall, because we accept their higher gradients for velocity, pressure, etc. Zaid, did it answer your question, or is it still not clear? Okay, great. Then let's continue. Let's go back to our settings. And we changed this number of cell levels to 4. And what we will also change are some parameters of step controls. You know, which are controlling the step where the mesh is snapped on the surface after deleting the inner volume. And we will just reduce the number of smooth patch to 3, reduce the tolerance to 1, double the number of iterations from 250 to 300, and we will reduce the number of relaxation iterations just to decrease the numerical effort. Since this mesh is very easy, it's very easy to create this kind of mesh because the geometry is very, very simple, and therefore there is no need for so many automatic mesh optimization steps. Okay, then let's go to the next step, which is creating the mesh by clicking the Start button. Great. Now our mesh will be computed, and since this can take some time, we have, for sure, I have prepared something for you guys. This project includes the same geometry with the same mesh settings, and I already computed the mesh, so we don't have to wait until the mesh is generated. And if you take a look, we have the same kind of refinements, the same coordinates, and even the same settings here. And the final mesh takes, if we take a look at the log file, needs 320 seconds to be computed and some additional time to copy it. And what we'll do right now, first of all, we'll take a more detailed look at the mesh. And here you can see the refinement zone, which was applied automatically. And let's take a look inside the mesh, creating a mesh clip filter. Now we can take a look inside the mesh. As you know, this can take some time since we have to really transfer the whole information to our servers and back. Guys, if you have questions, don't hesitate to ask me. I really want to answer every question, and there are no stupid questions. Just saying, because some people said that they're sorry for the question, because there are no stupid questions. Every question is good. Okay. And maybe not the very... Okay, now the mesh clip was generated, and we can take even a look inside the mesh, and then you will understand how this parameter number of cell levels between layers between cell levels change. For example, here you can see, and this is my buffer layer of 4 cells, and without the setting, with the default setting, it would only have 3 cells as a buffer layer here. You can play around with it and check it yourself, by the way. Okay, next step is to set up the actual simulation. So let's switch to the simulation designer and create a new simulation. Create. And we got a new question, by the way. Huin wants to know why intersection between 2 faces was refined. Can you please explain the question a little bit more? I didn't get what the point is. And I will answer it after, just in some minutes. In the meantime, we can start to prepare the simulation. First of all, we have to choose analysis type. For sure, it's fluid dynamics, and now we just take multiphase. And we have 3 settings which we basically have to define for this. And first of all, we have to make sure that the physics of our simulation we want to run. And in this case, first of all, let's discuss if it's laminar or turbulent. To reduce the complexity of the simulation, we decided to simulate a laminar case with a quite low fluid flow velocity. Therefore, we will do a laminar simulation. As you know, a multi-phase simulation is transient in any case. Therefore, we cannot change the setting. And there is a final thing you ask for, local time stepping. And the meaning of local time stepping is how you want, what kind of range you want for your time in your simulation. And there are basically several options. And in our case, we will not use this local time stepping, because it makes some things more complex for us instead of making it easier. So let's apply our settings. Local time setting off, turbulent model laminar, and transient. So we don't have to change anything at all. And click on Save. Next step is to choose the domain. We will choose the only mesh we have. And the mesh was added quite quickly. Okay, now let's create some topological entity sets to simplify our further work. First of all, let's start with the inlet phase, which is here. Call it inlet. Just 1 second. Okay, then let's try it again. Select the phase here, create a new set and call it inlet. Then this phase will be our outlet. Not our outlet. Sorry, it will be our... Wait. Here. And finally, you may ask yourself, why is that phase an outlet? And let's just quickly discuss this question. The reason why this is the outlet is quite easy. You should not forget there are two kinds of outlet. Something like a physical outlet where the water maybe will leave, which will not be this top phase. But an outlet can also be nothing less or more than the atmospheric pressure, which is also an outlet since we have two phases. And this is a decision depending on the actual setup you want to run. But in our case, we will define the top phase as an outlet. And only the top phase. Okay, therefore let's just do it. We can go on to the entity sets. Some stuff missing, and the final thing we will add is everything else should be a wall, so we'll select these two faces, this one and that one, invert our selection, and everything else will be called wall. Great. Next step is to add the materials, and here this might sound confusing, but first of all we will add two materials. The first material we'll add is air, and the second material we want to add, because we have two phases, is water. Hey guys, I'm back. Seems that I lost my connection. Can you see my screen again? Okay, great. Sorry guys. I'm right now at Toulouse at a conference with students, and internet connection is not as good as we thought. Anyway, so I think we were here, right, defining the initial conditions. And you have to imagine, since we have two phases, we have to define what is in which area. And we will make it subdomain based. We'll make a default phase fracture value of 1 and create a primitive Cartesian box. So that means we want to have here already water, and therefore we will add it like this. And this means that at the beginning of the simulation, everywhere is air, and only here in this area we have water. Next step is to define the boundary conditions. And this is maybe a little bit more complex on the first view, but don't worry. Let's create a new boundary condition and start with the inlet. And as I mentioned, this will be our inlet phase. We will have an x direction speed of 2 meters per second. And this is the more important thing. Here we can steer if we want to have pure water or pure air coming out of this inlet. Since you want to have water, make this value to 1, assign it to its inlet, save, done. Next step is to assign the pressure outlet. There we don't have to define any fraction because it's unknown here. And finally we have to create a boundary condition for the walls, which is also standard wall boundary condition. So just wall, no slip wall, apply it. Nice, really, we're already done. Okay, the next thing is we have to modify some numerical settings. The step-by-step tutorial will provide you later on with. That will be explained, so don't worry. So we will use 2 non-orthogonal correctors here. Also correct the solver, reduce the relative tolerance to increase faster convergence, and don't want to do any pre or post sweeps. Then we will change this one to a smooth solver and do the same for the remaining ones. Great. Click on Save to apply numerical settings, and finally we just have to set simulation setup. And now you will understand why we talked about pseudo time in the past. Since this is a transient simulation, here we have really existing physical time. And just to let you know, the overall length of our in x direction was 15 meters. So that means that after 7, and this length is the half, so 7.5. That means after 3.5 seconds, the wave should have reached this point. So therefore, we'll simulate from 0 to the end time value 0.5, the time step length of 1,000th second. And therefore, we have to limit Coulomb number, and we will use 16 cores, or let's even 32 cores, and increase the runtime and make adjustable, and the write control will be based on the simulation time of 0.2 seconds. So we will, every 0.2 seconds, we will write out the results. Click on Save. Now you're done. You can just check the simulation. And one thing is missing. It's the gravity, which we also have to add. Now everything is fine. And just one thing I forget. Air for sure is our phase 0, not our phase 1. Now we can just check the simulation, no problems, create a new run, and start it. Since this will take time until it's solved, for sure I've also prepared here everything. First of all, let's do just a quick wrap-up. I think I showed you first of all how to create the mesh. Next step was to set up the simulation. That means general simulation setup. We assigned the mesh, defined the material, this time 2 different material, and for every phase we defined our own material, we defined the initial conditions, especially the phase fractions, the boundary conditions, and we started the simulation. Okay, great. And just one thing. Yes, I just made one mistake I saw. Must for sure be minus 9.81. Thank you very much, David, for correcting me here. And then we can just create a new run and start it. Okay. Now let's take a look at the final results. Again, I prepared something for you. This project includes already the ready solution. So let's directly switch to the post-processor. And here, first of all, let's take a look at the convergence plot when the simulation is finished. And this looks completely different than the simulation plots of the CFD simulation we made before. And the question is, why? Well, you should not forget, every time step is calculated iteratively. And what we see here only are the time steps themselves. So this is just like the residual, final residual of the calculation of those time steps. And therefore you don't have to worry because the residuals are looking quite high. This is normal for a transient simulation. Okay, let's take a look now at the solution field. So if you open it, it will look like that, simulation. And what we do right now is to add an additional filter. This filter is called contour. And here we can define, for example, a value like 0.5. And then we will see the boundary phase, the interface between fluid and water, which is 0.5. And in addition, we can, for example, add this run again to visualize the outer walls. And then let's make a nice animation. Okay. And here we will just change this to a solid color, and we will add some opacity here. Or change the opacity is the right word, I think. Great, and now we can change the representation from pressure to velocity, for example. And then let's just start our animation from the first time step. And it takes a little bit, but now you can see here, we can see how the water wave is moving. And these waves you can see here are because of pressure fluctuations due to the walls, left and right. And now after 2.5 seconds, we have reached the step, and now you can see how droplets are forming and stuff like that. Okay. For sure, you can also apply other post-processing. Great, then I would say let's do a quick wrap-up. I showed you how to extract the surfaces, create contours, and you can apply all the other post-processing knowledge you learned from the last sessions to this example too. Great, then let's talk about your final homework. Your homework will be to perform such a simulation I created. You will be provided again with the geometry and a step-by-step tutorial, and you will investigate the influence of mass resolution of the CFL number on the quality of the multiphase simulation. The step-by-step tutorial is not finished right now. I will provide you with that, I think, tomorrow till afternoon. I will upload it and send an email to all participants of the workshop. Great, then thank you very much for being here. Now we have time for questions and answers. And just let me say, on behalf of the whole SimScale team, thank you for joining. It was the first time that we offered something like a master class or a workshop series which is targeting more advanced users. And we did it because of a lot of requests from users, and it was very successful. We have a lot of homework submissions, a lot of good questions and discussions. And yes, I just wanted to thank you for being here with us. Question is by Abhishek, he wants to know if spray modeling and droplet formation based on the same model and principle. Yes, basically both simulations are based on the Navier-Stokes equations. The only difference is that I need this couple condition, the volume of fluid method, to calculate it. Side wants to know what's the maximum number of nodes that SimScale can handle. Side, I think you're talking about cells. And cells, to be honest, from a technical perspective, nearly 100 million is the technical limit. And Gerasimos wants to know, is there a reason that you use such a long entrance length? Yes, there is a reason, because I wanted to show you how, based on fraction, in the beginning, even the structure of the flow is changing. Another reason is that the long entrance made it easier to have the right Coulomb number. You wants to know if you can set other boundary outlet instead of a top boundary. Yes, for sure. You should add the top boundary anyways to avoid these problems with atmospheric pressure, but you can add additional outlet, for example, at the rear wall. Then there is a question by Gutam. He wants to know, how about phase changing? Please give an idea. Can you a little bit describe this more in detail? Whoa, very good question by Levi. I nearly completely forget to talk about it. Levi wants to know, should we add layers at the wall? And that's a very good question. And let's do it like that. Let's make a small poll. Everybody who thinks we should use layers, please raise your hand. Oh. Most of people did not raise their hand, and unfortunately the people who raised their hand are wrong in this case. Not really wrong, but let me explain what the problem is, Levi. This is a very good question, basically. You're a good observer. Let's take a look at this sketch. When we have layers, we are stretching our elements. When we stretch our elements, we can get a problem, because then we have a complete different scale in x and y direction of the cell, for example. And if, for example, then, I think I have to draw it. You know, let's say we have this kind of standard cell. Okay? Length 2 meter, height 2 meter. And then the Coulomb number, let's say, should be 1. That would mean we have 2 divided by 2 delta. And let's say we are looking at that direction. And we have a velocity of 2 meters per second. Then the time step must be smaller than 1 second. But if we now have an element which has a height of 2 but a length of 8, for example, and the flow is going again in this direction, main direction, then we have 2 divided by 8 delta t, which is 0.5. That means delta t must be smaller than 2, which would be good. But what happens if for some reason at one cell the main flow direction is maybe like that? Then you will get a very big problem. And that's the reason why I would suggest not to use layer elements, because they will make it very hard to have the right Coulomb number. Because the basic meaning is, if you cannot increase your time step without increasing your local length step. And that's the reason why you should use uniform elements and not layer elements. Okay. Okay, the general question. What we cannot do right now with SimScale is simulate something like melting or stuff like that, unfortunately, but we'll work on it and we'll add it in the near future. The same for transition of water into steam. And we can also not simulate fire. But Christian, we had a customer who wanted to simulate some so-called fireboxes, and he just simulated air. If you're not really interested so much in the combustion itself, you can replace the combustion with a good heat boundary condition. And we also cannot do condensation. So we can only, that's a limitation of volume of fluid method, it's only working for non-mixing phases. Okay. Are there more questions? Yes, Zaid asked if I can again upload some theoretical data. Yes, I will again prepare some nice resources like YouTube videos, Wikipedia articles, other stuff I would like to know. Marco asked no, but that said that the velocity near the wall has an enormous gradient and that is necessary to model the real wall behavior. That's right, Marco. Therefore, simulating turbulent simulations sometimes become in a very, very big size. But for multiphase, and since it's multiphase and transient, the boundary layer is not so important for the total error. So it's possible to have also a good result without layers for multiphase, since for multiphase most of the time we have a low Reynolds number. But if you want, I would suggest, let's try it, guys. Just try to add layers and just post it into the forum and then we can discuss it together. Okay, great. Since all questions are answered, I would like again to thank you very much. If you have some more questions, you can also write it into the forum. I wish you a nice week. Goodbye. See you soon.